Okay, today we're going to go on to finish off momentum. So let's write on the momentum and finish this off. Okay, I'm going to give you an example, and that is the third type of collision. And through the example, I'm going to show you a very interesting question that I'd like you to answer and see whether you can get deeper understanding of the Newton's third law. Okay, so let's take a look. So let's go for a rather morbid example of having a truck which is 3m, mass 3m, moving at 30 meters per second. That's really fast, colliding with a car moving at 30 meters per second. Now, in most collisions, when they crash, usually they'll get stuck to each other. Yeah, so they get stuck and they move off with a common velocity. Now make a guess, where is that two objects going to move? Is it towards the right or left? Right. Obviously, right? So it's going to move towards the right. Now your task is to use conservation momentum to find the velocity towards the right. If you happen to want to ask what's the value of m, you don't need to know. Yeah, you don't need to know. Yeah, because it cancels off. I will actually say m3 u3 plus m1 u1 for obvious reasons. Yeah. Let's take a look. Yeah, right. 15. It is 15. Now, why is it 15? Let's do it systematically so you can see why is it 15. Yeah. So by conservation momentum, m3 u3 plus m1 u1 must equal to m3 v3 plus m1 v1. Now, because they're stuck together, what can you say about v3 and v1? Exactly, they're the same. So therefore, it's m3 plus m1 times v final. So if you were to work out the v final or v over here, it will be equals to 1 upon 4m multiplied by 90m. Why 90m? Because it's 3m times 30 plus 30 times m. Correct or not?
Minus 30.
Yes, correct. Please be careful, yeah? So it is minus. I know these are stupid tricks, but please, it happens in exams, yeah? So therefore you get your 15 meters per second. This is the easy part. The more difficult part is, who will suffer the bigger injury? The driver of the 3m truck or the driver of the m car? But this is the counter argument. I'm going to tell you that once one person, after learning conservation momentum and after learning Newton's law, he thinks that he learns and knows everything. So he's going to argue saying that, but Newton's third law says that the force on both vehicles are equal and opposite. And since forces on both vehicles are equal and opposite, then why they should suffer the same injury? But we know, obviously, the person who is in the M is likely to suffer a bigger injury than the person in the 3M. So how do you reconcile this? How do you explain to this smart aleck?
The forces are not equal.
Sorry?
The forces are not equal.
Then you're trying to tell me that Newton's third law is wrong.
No, as in the force the inertia of the 3m is not equal to the inertia of the...
Okay, so how does it lead to, okay, we got two situations over here. You got the inertia of the 3m bigger than the inertia of the m, and then you got the force on the vehicle on 3m is equal to the force on the vehicle m. This is Newton's third law. So how do you use those 2 points and arrive at the conclusion that the person in the 3m is going to suffer lesser injury? Right now we got all the things correct, so how do we, there's this leap that you need to take to link to the point that the force experienced by this driver is lesser than the force experienced by this driver. DM, you mean that the mass of the person actually changed? Scare the shit out of his pants or what?
So we can look at the deceleration, like, or the acceleration.
We're getting there, yes, correct. So let's take a look. Force by 3 on 1 is equals to force by 1 on 3. Let's ignore the negative sign, yeah? Let's just talk about magnitude. Now, we know that the m of 1 is lesser than the m of the 3m. Make sense? Yeah? So therefore, do you agree that acceleration, which is equals to force over m, you take this over this is going to be force experienced by 1 divided by 1. Is it bigger or smaller? You take this divided by this. Does it retain the sign or does it reverse the sign?
Reverse.
Yes, correct. Because it's 1 upon, so it's reverse. So the acceleration of 1 is bigger than the acceleration of 3. So what the driver of the M, the vehicle with mass M experience is a larger acceleration or deceleration as compared to the driver of the mass of the car with mass together. And then, assuming that the mass of the drivers are the same, you take the mass of the driver times A1, it will be bigger than the mass of the driver times A3. And that's why the force experienced by the driver is different. The force experienced by the car are the same. Because it's not driver knocks against driver. It's car knocks against car. The driver is only part of the car. So you have to be very careful about this. That the forces experienced by the car are the same, but the forces experienced by the driver are not the same. That's the subtle bit. Yeah? So what's the rationale of this story? If you have the means, buy a bigger car.
Yeah, truck.
Yeah.
Always crash a motorcycle.
Wow! What is this? You have the choice to crash the motorcycle. Oh man, this is really.
Yeah.
Hello! Mine! I think you choose my way of looking at it. Your way is a little bit crooked. Okay, so I love this question because it brings out certain deeper understanding of the application of the system. Okay, so copy this sequence. It has been laid out nicely so that it goes down in a nice way. It's not in your notes, this one. I'm quite sure. This one probably. But this one okay? So can you tell me how many kinds of collisions are there? There is elastic, there is inelastic, and this is what we call completely inelastic. Completely inelastic. Yeah? Why add a completely? Because it gets stuck together. Now why it's not quite sticky collision or whatever, I don't know. It's just the name given to it.
Okay, so you need to solve questions in between elastic and inelastic.
Do you need to solve questions between inelastic and elastic?
No, as in like when the collision is between the perfectly elastic.
Okay. That's a very good point. That's an excellent point. Okay, let's consider to answer your question in completely inelastic. Let me show you what it means. Let's go for an easy example. Yeah. So UU and MM. So the initial momentum is 0 because it's MU plus negative MU, and the elastic collision is an elastic collision. So do you agree that after the collision, if you solve for it using the UA minus UB equals to VB minus VB, you'll find that the two of them will move off at this kind of situation. So initial KE, final KE conserve, initial momentum, final momentum conserve. But look at this, in between, somewhere in between, do you agree that they come to rest?
Yeah.
Is KE conserve?
So it's just completely inelastic, right?
Okay. Whether it is completely elastic, inelastic, or completely elastic, you look at the final. But what he mentioned just now brings out a good point. Even if it is elastic in between the collision, it is actually inelastic. You get that point? Okay. So if it is elastic, say KE conserved over here, in between from here to here to here, it goes through this phase. Is the KE half mv squared times 2? It's not. It is 0. The KE is 0 at this point. So it is not elastic throughout. That's what I'm going to say. It is elastic before and after. And in between, it is most often inelastic. Cool? That's a good problem. Let me just entertain me. I'm going to give you a two-dimensional question. ASD, a little bit of ASD, yeah? A little bit. Let you just try and struggle for a couple of minutes, and we'll see how we go. So the two masses over here, same mass, this is U, and then after the collision, this one moves at this angle, this one moves at this angle. Prove that if it is elastic, this is right angle. Prove that if it is elastic, it is at right angle. VA, EB. Yeah. Glancing collision means it comes in over here, so on.
So, but it doesn't like meet at like 90 degrees, like it meets at an angle, then it goes.
Yeah,
Yeah,
so,
it'll be an
so,
angle.
so it will be something like this.
Yeah.
Yeah, something like this. Correct. It cannot be head on. If it is head on, it definitely move in one line. Yeah. Okay, I'll give you 2 minutes. Just push a bit. You're supposed to prove that if it is elastic collision and the two objects are the same mass, in this case, the angle between this and this is always 90 degrees. Always 90 degrees. Just give it a try. You never need to do this in IBM, so if you can't do this, don't reprimand yourself too much.
But so doesn't it depend on initial?
That's the beauty of
It
it.
always 90 degrees.
Always. The angle between the two final velocities always 90 degrees. And you find that the proof
As in,
is-
when you hit it at that, like, but then if you change the angle, then the ball takes, then wouldn't it?
Yeah, if you change it at different angles, it will still be it may be different angles, but it will always be 90.
Oh.
That means the angle between the final velocities. It may tilt this way, it may tilt this way, but it will always be 90. You can use conservation momentum in the vertical direction and the horizontal direction. You can use, I'm going to show you the solution here. One more minute.
So it's on.
Oh, wow. Can you share your idea? Stop. You're the kind of person who raise your friend's hands when
No, sir, you
teacher
just
asks for
stop it.
holiday.
It's damn shy to say, oh my. Some cosine
You can, but the method that I know of, it doesn't use that. A hint for you, why don't you draw a vector triangle? You know that momentum of A, let's call this A, let's call this B. Momentum of A final plus momentum of B final must be equal to momentum of A initial, yeah? Because it comes in the way. And then this is final momentum, A final momentum. So how do you draw a vector triangle to show this? Initial momentum of A. Conservation momentum says that this plus this must be equal to this. But how do you know that this angle is 90? Now let me show you if you use the conservation of KE. Yeah? Conservation of KE tells you that half times m u squared must be equal to half times m VA squared plus half times m VB squared. If you cancel away half m, can you see that u squared is equal to VA squared plus VB squared? Now, in a triangle where this squared plus this squared equals to this squared, oh, what do you say about this angle?
90 degrees.
Oh,
Wow. Damn. Okay.
it's neat, right? I mean, it's really.
I think it's in the
Yeah, it's really. That word is blushing, but looks embarrassed already. Okay, so just a. There are more different questions in this. Progressively, when you're ready, I'll just show you again. Cool. one final question, then we are done with conservation of momentum. It's elastic collision. So 3 kg, 5 kg, 6 meters per second, 2 meters per second, and 3 kg and 5 kg moves off with V3 and V5. It is an elastic collision. Solve for V3 and V5. This is it, right? This is absolutely within my business. Here.
The both are B5.
V3 and V5.
Oh.
V3 and V5. 3 kg 5. It's elastic collision. So there are 3 equations you can use to solve for the two unknowns. Conservation momentum, conservation of KE, and special equation I'll show you. Yep, use them. Do you know why you have to avoid using the half mv squared plus half mv squared equals to half mv squared plus half mv squared? Do you think that it's easier to handle square or linear terms? Obviously, right? So whenever possible, avoid using the square.
Yeah.
Use a special equation.
It's damn weird.
So what is it? Question?
Independent of mass.
Yes, exactly. You are correct. It is. But there are many weird things that happen in this world. Like quantum physics. Like electron, you don't know whether it's a wave or particle. There are many weird things like people be very, very careful on the negative sign. Be very, very careful. It will cost you dearly if you're not. Shannon, are you still feeling cold? V3 comes to rest, that's very interesting.
So is it?
Yeah. V3 comes to rest. That's very interesting. I give just some random value. V3 actually came to rest. That's weird.
Oh, right.
It's very weird.
Wait, so is it negative 6?
Yeah, it is. Because I've added the two values together. The first equation and the third equation.
Yeah. Oh,
Yeah, negative 60.
If you add together, once you get 63.
But that's weird. Then V5 will be moving continuously in the negative direction, which is
That's
passes
also
through
you get
the
63.
3 kg.
Which is 8.
Oh, yeah.
Should
Right?
minus.
So
So you should minus, if not you get 6v3.
Oh. Okay, let's see. Which one? It's the first and the third.
Yeah, as in first and third equation, if you say you added them together, but then you get 6v3 instead of 0.
Okay, this is 18 minus 10, right? 18 plus minus 10 is actually 8.
Yeah.
Right? So then this one, V3 minus V5 is U5 minus U3. So it's minus 2 minus 6. So it's minus 8. Yeah. So what I do is that times 3 on both sides, then I minus 24. Then I take this. Oh, minus.
You need to minus,
of
yeah.
course. Of course, what am I doing? No mistakes. Minus, therefore this is 16. Then therefore this is 2.
Okay, should only be 32.
Which makes sense, and V5 bounces backwards. Then V3 will be 2
8 minus minus 3.
plus 2.
Oh yes, yes. That's why it's 32, not 16. Because it's 8 minus minus 3.
Oh, okay, it's embarrassing. Yes, correct. And therefore this is 4. Right? Is it okay now? So therefore V3 will be minus 8 plus V5. That will be minus 4. Maybe. And now it's good. So minus 8 and then minus 32, 4. Yep. Makes sense now. This one V3 comes, the rest cannot be. Okay. So this is, remember, whenever you have elastic collision, my recommendation for you is always use the spectral equation. Very useful, regardless of mass. Alrighty, I'll stop here for a while. I want to use some questions.